We next explore the concept of thin film interference. So when light travels through an object that's transparent, most of the light does travel through the object, but a small amount is reflected. And you've all experienced that if you've ever been indoors at night and you look at a window, right? Inside it's lit up, and you look out a dark window, you see your own reflection in that window. Even though the window is not a mirror, it's not designed to be a reflective surface, some of the light that tries to go through the mirror is reflected by the inner surfaces between the air and the glass and reflect back towards you. And if you have multiple pane mirrors, windows, then sometimes you can see multiple reflections. So we can use that to our advantage in certain situations. And what's happening is you have a ray of light coming in and striking the mirror. And I put it at an angle. Imagine going straight in, but then these arrows would be on top of one another. It'd be harder to see. So imagine that this is a very, very shallow, very close to 90 degrees coming in on the normal. A ray comes in. Some of the light reflects off the surface. Let's pretend this is air and glass. Some of the light reflects off the surface. It comes back to your eyeball. We'll draw your eyeball over here. Most of it transmits through the glass. But then when the ray hits the boundary between the glass and the outside air again, assuming that's air, it's a fish tank, it could be air to glass to water, for instance. So once it strikes that interface, most of it passes out, but some small amount is reflected. When that hits this interface, you get some reflected, but some of it passes out. So what happens is you have two rays here. This ray traveled the extra distance, basically twice the thickness of the glass, traveled the extra distance to come out, whereas ray 1 just reflected off the surface. So these two rays here can interfere with one another. If these come back together in phase, the light will look bright at whatever wavelength we sent into this grouping. So for instance, if the thickness, or twice the thickness, because it has to travel through the thickness and back, if twice the thickness is equal to one wavelength of light in the material, which is again lambda sub n, the wavelength of light in that material, if it's one full integer wavelength of light, then you'll get constructive interference. So what happens is when 2 times the thickness is equal to some integer number of wavelengths, let's say lambda or 2 lambda sub n, or 3 lambda sub n, and so on. This is constructive interference. Ideally, if it's just due to the change in thickness. And then if twice the thickness is equal to some half value of the wavelengths, lambda n over 2, or 3 lambda n over 2, or 5 lambda n over 2, raise our eyeball, this would give us destructive. Remembering that lambda sub n is equal to lambda over the index of refraction of the material you're going through, right? So this is glass. The wavelength of light, let's say we start off at 500 nanometers of light coming in, so blue light coming in. The wavelength in this material depends on the index of refraction because that changes the wavelength of light. The bigger the index of refraction, the shorter the wavelengths. So by changing the type, not only changing the thickness changes the amount of wavelengths you have in this extra step, changing the index of refraction also changes the wavelength of light, changing the amount of wavelengths you experience as you travel this extra distance. So there are 3 things that can change the type of interference that you get. If you get constructive interference, or you get destructive interference, or somewhere in the middle. The first is the reflection off of a higher or lower index of refraction material. That can actually change the phase of the wave. So here we have a ray coming in air, hitting glass, and then bouncing off. This reflection is off of a higher index of refraction material. Air has an index of refraction of 1. Glass, let's say it's around 1.5. So this reflection here will cause a phase shift of half a wavelength. which I list down here. So expanding on number 1 in the red, when light reflects off a medium with a higher index of refraction, it experiences a 180-degree phase change, or in other words, a shift of 1/2 of a wavelength. So if the wave comes in at its peak and it bounces off material of a higher index of refraction, it starts off at the trough and it continues on. If we flip that and it bounces off a lower index of refraction material, that phase shift doesn't occur. Like, for example, here. Here the ray is in glass. It bounces off of a glass-air interface, so it's bouncing off the air medium. Air has a lower index of refraction than glass, therefore that ray will not experience a phase shift. So these two rays, without worrying about the thickness of the material, without worrying about the index of refraction of the glass, just knowing that it's greater than air, I know when these two rays come together, they're going to be out of phase by 1/2 at least, because one of them will be reflected off of a higher index of material that will shift the reflection by 1/2. The other will not be set up off a higher index of refraction material, so they're going to be out of phase, giving you completely destructive interference if the thickness is effectively 0. However, the thickness is not 0. So there's other things that can create interference changes. Number 2, the extra distance ray R2 travels. So this extra distance, basically twice the thickness. If I change the thickness, hopefully you can see that I can change the length that ray 2 has to go before it meets back up with ray 1. I can make it 1 full wavelength, or I can make it 1.5 wavelengths, or 2 wavelengths, or 2.5, or 3 wavelengths. So by changing the thickness of the material, I can also change whether you get constructive or destructive interference, or something in between. And then finally, the index of refraction of the material. So if I don't change the thickness, but I just substitute the material, let's put water in here, or let's put glass, or cubic zirconium, or diamond, or whatever, I can change that index of refraction a bit. That will change the number. While it doesn't change the path length, it does change the wavelength of the light when it's in that material, which would change when the wavelengths come back together, whether or not they're in phase. So the 3 different things you have to worry about when calculating whether or not you get constructive or destructive interference for thin films. So these 2 equations basically just talk about the last 2 things. For constructive and destructive interference from these 2 equations, just take into account these 2 things. You then need to worry about whether or not there's phase shift due to the reflection. So if they're both reflected off higher index of refraction material, let's say it's air to glass to diamond, well then each of these reflections is off a higher index of refraction material. Each of these reflections will go through a phase shift of λ/2, so they'll be back in phase. Right? If you shift both of them by the same amount, they're still in phase. So these 2 equations are accurate. This will give you the constructive interference. This will give you the destructive interference. However, if we go back to what we had before, air to glass to air, well then you only get a phase shift of 1/2 off the first reflection, not off the second. So basically these 2 equations are flipped. The equation below will give you constructive interference. The equation above will give you destructive interference because of that one ray was phase shifted by 1/2, the other ray wasn't. So it's a bit complex, and your book doesn't do a great job of going through it. Look at this video, look at the Khan Academy videos I've linked. Hyperphysics is another wonderful website that goes through this in detail. It's more calculus-based, but not all of the explanations are. You don't need calculus to understand these types of simple algebraic relationships. Now, why use thin film interference? Why do we care? Well, we can take advantage of thin film interference. Well, you've experienced it, all of you. If you've ever looked at a soap bubble and you've seen the sort of the colors in a soap bubble, the pinks and the blues in a soap bubble, that's due to thin film interference. If you've ever looked at the side of the road after a rain and you can see the oil slick from the oil, gasoline, and car tire rubber that was on the road that got washed off into the side puddles, the polluted water, oil slicks create a very thin film over water. So there's water, oil being less dense, so create a thin film over the water. That thin film causes thin film interference, giving you that rainbow shimmering effect of oil on water. So you've probably all seen thin film interference. But we can take advantage of that, and you might have already taken advantage of that, for instance. If you have glasses, sometimes you're asked, do you want an anti-reflective coating on your glasses? That coating is specifically designed to prevent these reflections, meaning that they want destructive interference here. They want the light to go through, not to bounce off. So you have laptops. Laptops, for a while, the laptop screens had anti-glare coatings versus the ones that reflect just like normal glass. Some like the anti-reflective, some don't, but that option is enabled because of thin film interference. So thin film interference is actually very important when dealing with optical instruments, coatings, and things like that, anti-reflective coatings, and so on. So this is a summary of thin film interference.